So in chapter 6, we're going to be talking about systems of linear equations, or systems of linear equations. So we first need to know, what in the world does that mean? Well, a system of equations is a set of two or more linear equations containing two or more variables. Set of two or more linear equations, at least two, but it can be more, and it contains two or more variables. What are our most common variables we use? X and Y, right? X and Y. How many variables is that? Two, okay? So those are going to be the ones we're usually going to be dealing with. So sometimes linear equations are used, or systems of equations are used. They can be used to represent situations to solve problems related to consumer economics, like buying things and whatnot. Finance and geometry are some different times they can be used. We have a few different ways we can solve systems of equations. We're going to be talking about three different ways we can solve systems of equations in this chapter. The first one we're going to talk about is graphing them. So, solving by graphing, if two lines are graphed, they always meet at one point, exactly 1 point, unless they are parallel or the same line. So if two lines are graphed, you graph two lines, they're either always going to meet at 1 point or they're parallel or the same line. Remember, parallel means they don't intersect, and if they're the same line, it's kind of like they're just like stacked on top of each other. So the point where two lines meet is called the intersection. Think about kind of like two streets when they intersect. It's called an intersection. And we write it as an ordered pair. How do we write ordered pairs? What comma what?
X comma Y.
X comma Y, exactly right. We write it as X comma Y. And we have some different steps here that we have for solving them. These can be helpful to kind of refer back to, so if you get stuck on how do I solve this, Mr. Kostel, we have steps here for us. First step, putting both equations in a slope-intercept form. We find it much, much easier to graph when you have them in slope-intercept form, so put them in slope-intercept form. But it says if necessary. Why do we think it says if necessary?
Because sometimes you might have to.
Exactly. Sometimes you might have to, sometimes you might not. Sometimes they're already going to be in slope-intercept form. Sometimes they won't be. That's the way you check for. Second step, we would graph the first equation, and you can use the ruler to draw a line. You don't have to. But if you want to, I do have rulers back there. You can use a ruler to draw an exact line. On these, I actually do recommend it though. Even though so far when we've been graphing, I haven't been. I recommend it on these because we need to be a little more exact, and I think we'll see why. Step 3, graph the second equation and use a ruler to draw that line. Step 4, write the point where the two lines meet, the intersection, and that's your solution. We call that the solution to our system. That's the X and Y, the ordered pair that works, that makes it work. So we're going to go ahead and try this.
Do you want to pass on the rulers?
Oh, yeah. Thank you.
Yep. I get first pick though. So let's just.
Okay. So look at this first one. Example 1. We have two equations, right? When we write a system of equations, notice this kind of little bracket thing we put at the start of it. We put that there to denote or to show that this is a system that we're dealing with. Okay, it's a system. They go together. So that's just some kind of notation we see when we have this. These equations, what kind of form are they in? Slope-intercept form. What's our first step say? Step for solving. What's the first one say?
Put both equations into slope-intercept form.
Yeah, put them both in slope-intercept form if necessary. Kale, do we need to put them in slope-intercept form? No, why not? They're both already in it. Awesome, we already did one step. Woo, let's go, okay? Step 2. Graph the first equation using a ruler to draw a line. The first equation, y equals negative 2x minus 1. How do we graph this? William. Okay, go down 2, then right 1. And you can make a third point as well. How would you make that point? If you make a third point, you can go up 2, left 1, or down 2, right 1 again, right? Okay, and then I'm going to use my ruler, and I'm going to connect these 3 points.
Shouldn't we do more than 3?
You can, yeah, feel free to do more than 3.
Because what if we like meander all the way top of the line?
Yeah, feel free to do more than 3. You can do as many as you want on these. And because you're doing slope, you know exactly where it's going to be. So you can feel free to do a ton of them. On my notes, when I went through them, I did 6 points for this line. You don't have to, but you can. Now just to make it so we can tell the difference a little easier, I'm going to do the second one in blue up here, just for showing purposes. How do we graph the second line? Jacob, help me out with that.
Well, we start at 5 because that's the y-intercept.
Okay.
And then we go up 1 because there's no, well, it's just basically just 1x, so up 1 over 1.
Oh, which
To the
direction
right.
do we go?
Up and right.
Oh, whoopsie daisy. There we go. And then what if we went down? What if we went down 1?
Then you go left.
Yep. So let's go ahead and connect these points as well. Oop, kind of slanted there. Where do these lines intersect? Graydon. Negative 2, comma 3.
I did not get that.
Where does your first line look like mine does in the red?
Yes.
Okay, let's see, let's ring that up, let's forget. Does your blue line look like mine?
Yes.
Where do they intersect?
Like right in the middle of 2 and 3.
Like,
She has it.
My line is off.
I think this first line's a little off.
yeah. So something to be really careful about here. Something to be really careful about here is we have to make sure our lines are exact. So, for example, if we were to have a line here on accident in the red, we were to have a line like here. Is that green line that far off of the red one? Not really, it's pretty close, right? But is the intersection different? A little bit, it might make you think it's somewhere else. So we have to be really, really, really careful when we draw our lines that we go exactly through our points. That's why we have to be really careful with that. And that's also why we do this next step. We do a step where we go through and check it. So to check it, we take this point and we plug it in. We say, hey, let's take the first equation, y equals negative 2x minus 1, and let's plug in negative 2 for x and 3 for y. And if this works out, then it's correct. And we'll look at what I mean by if it works out. everybody to be at this step. Everybody to be at this step.
Skyrim's actually trash.
Okay, let's go back to this.
Yeah, you like Fortnite. You can't have an opinion of what many games are trash. I actually play NBA 2K19.
Okay.
Okay, so you don't have an opinion what games are trash. You're not helping your case.
So, does everybody understand how we got to the step of plugging things in?
Yes.
We took the first equation that was up here that we're dealing with, and we plugged in our x and y solution we found.
Do you keep the y with
Say that again.
the 3? Do you keep the y with the 3?
Like, do we put this one into here?
No, but do you like carry down the y with the 3, which is 3y?
Oh, no. And just like you don't put so this -2 here is a -2 in parentheses. So the 3 goes in place of the y, and the -2 goes in place of the x. Good question. Now we want to look to simplify. Well, 3 is just 3. What's -2 times -2? Positive 4 minus 1. Okay, what is 4 minus 1?
3.
Does 3 equal 3? Okay, we got it. That means it works. That means the solution works for this first equation. So we're going to put a little check mark. That's just saying, hey, we checked it and it worked. Awesome. We're also going to check our second one. We're going to take this one, y equals x plus 5, and we're going to plug our solution in here as well. So we're going to plug 3 in for y, -2 in for x, and check this one as well. What's -2 plus 5? -2 plus 5. 3. Does 3 equal 3? Yeah. We checked it, it works. So, if we were to get anything other than 3 equals 3, or anything other than something equals itself, it doesn't work. Because say if we got 3 equals 4, it doesn't work. But that means this solution works for this equation. It makes it true. And if it works for both, it's our answer. So this was our solution in fact. We checked it and we were good. So checking it can help. If we make some simple errors, we can catch them by checking it, because it wouldn't work out if we did that. Questions on this first one? Okay, let's go over the second one a little bit. Let's try the second one a little bit. So, this first line, -x plus 3y is equal to -9. What's our first step for graphing these? Put both equations in slope-intercept form if necessary. Is it necessary to put them in slope-intercept form this time? Yes. Yeah, okay. So what variable are we going to solve for? Y. So let's take this first equation. I'm going to draw an arrow, say I'm going to take down here. -x plus 3y is equal to -9. If we're solving for y, what's going to be our first step, Christian? Okay. Well, what do we want to get rid of if we want y by itself? We want to get rid of something else. Yeah, so how do we get rid of this x? Okay, how do we move it? Okay, we'll add it. It's currently subtracting, so we'll add x. Because what's -x plus x? Nothing, it's 0. Gets rid of it. That's awesome. So we have 3y is equal to x minus 9. Is y 100% by itself yet? No. How do we get it there, Josh? Divide by 3 on both sides. So y is equal to x over 3 minus what number? 3. So we did our first equation. We got our first equation in slope-intercept form. Let's get our second equation in slope-intercept form as well.
Wait, we didn't graph it though.
You're right. We're going to graph it in a second. So So we'll get them both in a slope-intercept form, then we'll graph the first one, then we'll graph the second. Good question. So let's do the second one. Let's get the second one in the slope-intercept form as well. Let's go over here with our work. 2x plus y is equal to 4. What would be our first step in moving things around to get y by itself then?
Divide the 2x.
I don't think you divide it. Is 2x being multiplied to something?
Now you subtract 2x.
Yeah, I like that move more. So we'll subtract that 2x. So just like here, we moved the x away from the y to start. We're going to move the x away from the y. Because 2x minus 2x is 0. So we're left with y is equal to negative 2x plus 4. Devin, is y by itself now? Is there anything on the other side, on the side of the equation with y? No. So I would say it's by itself. Okay, yeet. So we have our two equations. Let's graph this first one. Y equals x over 3 minus 3. Justin, help me out graphing this one. Let's see what's done that. This was good.
Alright, so go to -3 on the y-axis. Go up 1, right 3.
Very good.
Then from -3, you go down 1, left 3.
Let's use our ruler to connect them. So we're very, very careful here. We did the -3 one. Okay, questions on graphing that first equation? Betsy, help me with graphing the second equation. Y equals negative 2x plus 4. Okay. Okay, I agree. Could we make a third point too? Okay, so we could go maybe up to left 1, or we could go down to right 1 again. We can make as many points as we wanted, right? We said that earlier. We can make as many points as we want. So then we'll use our ruler. We'll be very careful about connecting these points. Do we see a very clear intersection for these lines? Yeah, where is it at?
3, -2.
3 left and right, 3 right, and 2 down. So 3 comma negative 2. So our solution is 3 comma negative 2. And once again, we'll check this. We'll make sure we are right. We'll validate our work. So we'll first check this one in the purple, our first equation we did. And we're going to plug it back into our very original equation before we started moving stuff around. Does anybody have any ideas as to why we would choose our very original equation? Justin?
Because sometimes when you move something around, like this, say you had to add x to it, that would turn x to a positive. You would need x to stay negative so that it stays like how it was before.
Not necessarily. Actually, it could work in either. But I like the train of thought you're going on. It's a good train of thought. Yeah.
Can I go to the bathroom?
Yes, you may. Fill out your password, please. So the reason why we'd want to plug it into our original instead of one of our new ones is when we change stuff around, sometimes we make mistakes, don't we? That happens. Okay, I make mistakes, you make mistakes, it happens. Because of that, we want to plug it into our very original equation because this is what was given to us. We know there's no mistakes in this one. So that's one we're going to plug it back into. a safe way to go. So we'll take this equation, negative x plus 3y is equal to negative 9, and we'll plug in these points. So we'll plug in 3 for x. Remember, I always plug things in parentheses, because I think it helps with our signs. Derek, what's the negative of positive 3? What's the negative of positive 3? What's this become? What's this first number become? It's currently like a negative times 3. Okay, just negative 3. And what's 3 times negative 2? Okay. And then we have this negative 9 over here. Devin, what's negative 3 minus 6? Negative 3 is becoming more negative. Not quite. So they're both negative. They're both negative. You already owe me $3. I lend you 6 more. How much do you owe me total? 9. So it ends up being negative 9 is equal to negative 9. Same number on both sides. It checks out. We're good. We'll try our next one. Questions on this one though before we go on? Grace?
I did not get that. I'm so confused.
Get the solution? Okay, what do
I
you
I kind of fell behind.
Okay.
So I was kind of like on my own, but I did not get that.
Okay.
Not even close.
So what's your first line?
It's like that.
Okay.
But I don't know if I'm just off or something. But I got
Yeah.
like 5 negative 1.
So here when you subtracted 2x, you just had a minus x here. So that should be minus 2x. That makes sense? So that changed up your slope here. And this first line is good though. So that changed up your first slope. Thanks for asking. So let's go ahead and I want you guys to check the second one on your own. I want you guys to check the second one on your own. So I'm going to take the second equation, 2x plus y equals 4, plug in this solution and check it and tell me if it works. Actually, sorry, stay silent after you get it. But to see if it works.
Wait, so what do I do?
We checked our first solution. We checked our solution, excuse me, in the first equation. So we plugged it in, and we got, hey, negative 9 is equal to negative 9. It works. It's the same number. So we're checking it in our second equation now. We're taking this equation, 2x plus y equals 4, and we're plugging in our solution to see if it works. So when we plug this in, we have
Wait,
2
what is it?
times.
I'm so behind.
Where are you at right now?
I am trying to figure out my solution
Okay.
because it's wrong.
So it'd be when you graph this, let's make sure we have that slope that we talked about, and it'll go through this point.
It's fine.
have 2 times, what's our x here? Plus our y is -2 equals 4. What's 2 times 3? 6 plus a -2 is equal to 4. So what's 6 plus a -2 or 6 minus 2? 4. Does 4 equal 4?
Yeah.
Awesome. Our solution works. You checked it, it's good. That's what I think is a really nice thing about algebra and math in general is oftentimes you can check your work to see if it was right. You can know instantly, did I do this right? Because it worked or didn't. If it worked, we did it right. Once again, if we had gotten down to something in this equation where it was 3 equals 4, does 3 equal 4? No, 3 does not equal 4, so it wouldn't have worked. But we didn't get that. We got 4 equals 4, which is true. That does work. We're going to go to the next part right beneath this where it says identifying solutions of systems. So if we're given a system of equations, we're given 2 equations, and we're given a solution. We're trying to tell whether the ordered pair is a solution or not. So we're trying to say, okay, instead of trying to find the solution, we're trying to say, is this solution right? Does this one work? So we have 3 steps for this one. We'll plug the point in for x and y in the first equation. We'll plug it in for the x and y in the second equation, and it has to make both equations true. So we plug it into the first equation, and we solve to get to the end, like we did when we checked. And we do the same for the second equation. And if they both work, it's a solution. If one or both of them do not work, it's not a solution. Both of them have to work. So let's try this first one. It's more plugging in like we were just kind of doing. So we'll take this 4, 1, and we'll plug it into x plus 2y equals 6. Blake, can you tell me how we would plug this in? I agree. The 4 would be where the x is, because that's our x coordinate, and the 1 would go where the y is, because that's our y coordinate. So we put that in the equation. From here we would solve. What is 2 times 1? 2. What is 4 plus 2? 6. Jacob, is 6 equal to 6?
Yes.
Awesome. So the first one worked. Let's try the second one. Gotta check both. So take the second equation. X minus y is equal to 3. And once again, we'll plug in the same solution because we're checking it for both. Jacob, eyes open, please. Thank you. Okay. Sam, how do we plug this one in?
4 goes in
Okay. So we end up having 4 minus 1 equal to 3. What is 4 minus 1?
3.
Is 3 equal to 3? Is this a solution then? Yeah, it worked for both equations. It must be a solution. So we say yes. And so our answer is just this yes. But what's above here is our work that proves that. What I want you guys to do is I want you to do number 2 by yourself. I want you to do number 2 by yourself. So go ahead and work on number 2, please.
Can you come help me?
So what's your y?
Or no.
I want you to do all of number 2. We plug this one in. Let's try this first equation here. X minus 2y is equal to 4. If we plug this in, we plug in the 2 for x. We plug in this negative 1 for y. What is negative 1 times 2? What is negative 1 times 2? Negative 2. So that would be like minus and negative 2. What happens when you have 2 minuses in a row? It becomes positive, right? You add the opposite. Whenever you're subtracting, you add the opposite of this number. The opposite of negative is positive. What is 2 plus 2?
4.
Does 4 equal 4? Awesome. Hey, we checked the first one. Do we even need to check the second one? We checked the first one. It worked out. Are we good?
Yeah.
No, you have to check the second one.
No, you have to check the second one, right? Okay. So we go through. We check the second one. Because we say, oh well, you know, just for grins and giggles, I suppose, right? So we'll plug in the 2 for the 3 for x. We'll plug in negative 1 for y. And we say, okay, what's 3 times 2? 6 minus 1. Does 6 minus 1 equal 6?
No.
No, because 5 is not equal to 6. So is this one was a solution because it worked in both. Is this one a solution?
No.
No. So our answer is just very simply no. This system has a solution, but this is not it. This system has a solution, but this is not the solution. So it's not that there is no solution. It's not no solution. It's just that this is not it. So you say, is this a solution? No.
No.
Does that make sense, kind of the difference between no solution versus this just not being the solution?
Yes.
Okay, good. Let's go ahead and flip that page there. Not yet. If 2 lines are parallel, 2 lines are parallel, they have 0 solutions because they never cross. Remember, parallel lines are kind of like the train tracks or like the lines on these flags. They never, ever, ever cross. They won't intersect. If they don't intersect, can they have any solutions? No, because where was their solution before? When they intersect. If we go back here to these examples we did, the solution was where they intersected. If there is no intersection, there is no solution.
Wait, so this one's gonna have both of them on the right?
Say that one more time, please.
So, like, you
Oh,
know,
the possible solution?
Yeah.
There would be no possible solution, or if you tried one, it wouldn't work. Correct.
so it's like, that's how you tell if it's no solution or if it's.
So the only way we know, the only way it would be 0 solutions is if they're parallel. And parallel lines, what do they have going on with their slope? What what do we know about the slopes of parallel lines? The lines never cross, but the slopes themselves, the numbers are the exact same. So if they have the same slope, we know there's going to be no solution because it means it's parallel. So that's how we know mathematically is we look at the slopes. Now our other things would be if two lines are coinciding, that's a big fancy word for meaning that they are the same line. For us, that just means that they're the same line. Two lines are coinciding. That means they have infinitely many solutions because they share every single point. If they're the same line, every single point they have is an intersection because they share every single point. So everything's a solution. Let's go through these examples here. That first example. Okay, we're graphing a system of equations trying to solve. What's our first step when we graph a system of equations trying to solve? Put them in a slope-intercept form if necessary. This top equation, do we have to put it in a slope-intercept form?
Yes.
Let's do that. What would be our first step to get it into slope-intercept form? Subtract 3x. Move our x over. Two y is equal to negative 3x plus 6. One more step to get y by itself. Christian, what would you do to get y by itself? Okay, and how do you move this 2? Divide. It's currently multiplying with our y. We'll divide it to get rid of it. So it'll be with y is equal to negative 3 over 2x plus 3. Remember, we divide this whole side by 2.
Please excuse the interruption. Please, all seniors report to the auditorium at this time.
So now is this equation in slope-intercept form? Awesome. Is our second equation in slope-intercept form? Oh, that's the second equation. That's nice. Whew. Okay, so let's go ahead and graph this first equation then. Kale, help me graph this first equation. Okay. Awesome. Then we can also go up 3 in which direction for the 2? Left. So let's go ahead and use our ruler to connect these lines, or connect these dots to form our lines, I should say. What was that? We had it at 6, but when we divided this whole side by 2 to get y by itself, 6 became 3.
How did I miss that? Oh my goodness.
There we go. Okay, so now we graph our second equation. Our second equation, y equals negative 3 over 2x minus 1. Krista, help me graph this one. Okay, we could also go up 3 in which direction too? Correct. Let's go ahead and plot our graph, connect these points with our ruler. What do we notice about these lines? They're parallel, they never intersect. So how many solutions are there?
0.
None. So our solution is that there is no solution. Or we could say no real solution. Or we could say no solution.
Can we do NRS? Because that's what we did last year.
Yep, any of these 3 would work. Any of those 3 I circled there at the bottom would be acceptable explanations. Now, could we have known when we had these both in slope-intercept form that they were going to be parallel?
Yeah.
How?
Because
The
the slopes are the exact
slopes are the same. So if we catch it early, awesome. If we don't, we graph it and we catch it now. Question on that first one.
So you wouldn't have to graph it to tell it's that, but you wouldn't have to.
Are you gonna make us graph it?
Yeah.
Correct, but but we have to be careful that they aren't coinciding in that case. And we'll talk about that right now, actually. And I'll circle back to answer your question. So, if we look at number 2, our first step is to do what with these equations? Slope-intercept form. Is the first equation in slope-intercept form? Awesome. Is the second equation in slope-intercept form? Darn. How can we get this in slope-intercept form? Grant said, hey, we need to move this x, we're going to subtract 1 over 2x. We end up getting negative 2y is equal to negative 1 over 2x plus 4. What's our next step to get rid of, or to get y by itself, rather? Jacob. You're stretching, but I'm counting it. How do we get y by itself?
Divide both sides by negative 2.
Divide both sides by negative 2. Negative 2y divided by negative 2 is just y. What's negative 1 over 2 divided by negative 2?
Negative 1/4.
Positive 1/4. So if we take a half, if we have a half of something, so we take a circle, we cut it into half. So we're just looking at this left half now. What happens if we cut this half into 2? How much of this whole thing do we have left? A fourth. So that's how we end up with 1 over 4. Does that kind of make sense? What we do mathematically there is we take this, when we divide by the 2, it's the same thing as taking negative 1 over 2 times negative 1 over 2. When we multiply fractions, we multiply straight across. Negative 1 times negative 1 is positive 1. 2 times 2 is 4. Mathematically, that's how that works out.
You can just know that half of a half is a fourth.
Correct. And what is 4 divided by negative 2?
2 or
Negative 2. So we have our first equation, y equals 1/4 x minus 2, and we have our second equation, y equals 1/4 x minus 2. Wait, what? They're the same thing. How do you know they're the same, Ben? The equations are exactly the same. They're both y equals 1/4 x minus 2. So if we graph one, did we automatically graph both?
Yeah, sure.
Hey, let's go ahead and do it anyway, though. We go down to negative 2. Woo! We go up 1, we will go right 4. We go down 1, we will go left 4. We connect our points. And that is both lines. We just graphed both lines in one because both equations are the same, right?
Bam.
How many solutions does this one have?
Yes.
Infinitely many. This is the solution. This is the solution. Solution, 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 solution. All of them are solutions. So you can say it has infinitely many solutions, or you can say all real numbers. That is an acceptable way to say it as well. S is not numbers.
ARN.
Okay, so last year we did NRS for no real solution or IMS for infinite.
That's
But
fine
there
by
was
me.
one more, but I can't remember what it was.
Quattro.
I'm not sure. But these NRS and IMS would both be good by me. So that's how you want to word it. Awesome. So Ben, back to your question. When you were saying, Ben was asking earlier, hey, if we know from this first one in the parallel lines, if we know that these slopes are the same, that this has a slope of negative 3 over 2, this has a slope of negative 3 over 2, we know they both have the same slope. So do we even have to graph it to know? Well, the only thing we have to be careful about is that they're not coinciding. But if they're coinciding, we know they're going to have the same y-intercept as well. Did these have the same y-intercept? No. This one had a y-intercept of +3. This one had a y-intercept of -1. They were going to be different. So if you can tell without graphing, awesome. But if you need to graph, go ahead and graph. There are graphs